Physics 1 Lab 2. My name is Aditya Potlery. And the purpose of this lab is to understand more about Newton's laws and how this relates to the motion of falling objects, and students will understand how drag and gravitational forces operate using a real example. The fundamental ideas are basically the force of gravity is negative mg, but the acceleration due to gravity is negative g, and the drag force is proportional to the velocity squared multiplied by, and the actual drag force is, you can see on this is a bunch of constants like the drag coefficient, air density, and the area of the thing that you're dropping, which in this case is a plate from a certain height, in this case around 1.65 meters, and it's dropped with initial velocity of 0 to drop from rest. So you can see in the drag model, it's just force net equals force drag minus force gravity in the gravitational model. Force net equals force gravity. After doing the experiment, you can our initial results are that, the real result seems to match the model with drag far more closely. The reason that I use this equation to model drag is that it takes into account the most important aspects of drag, which is, the coefficient of the object that you're dropping, the area, and the air density, along with proportional velocity squared, which is a requirement. The system is the plate, the air it falls in, the hand it's released from, and the ground it lands on. You can kind of account for these things. And then the surroundings are all the unaccounted objects / people and forces and around the plate in the GTE lounge, as seen in the picture. The plate is dropped from rest from a height of 1.65 meters around roughly, and the fall time was around 0.9 seconds. I calculated the drag force using the equation shown in previous slides. I manually entered in the constants, and I used force gravity and the force drag to calculate force, which I used to update velocity, which I used to update position. Every time delta, I would kind of update all of these in the loop, and they would all kind of update each other. Force updated velocity, velocity updated position, and so on. And these are my real results. You can kind of see the real position and the drag position were very, very close. In fact, they're all very close until about 0.2 seconds, which you can kind of see as velocity grows in the drag model and in the real world, there's going to be more of a difference because the drag force increases as velocity increases. So, yeah. The reason that there might be a slight difference is because of slight differences and, the way that the area of the plate was measured. It's not an exact circle. Also, I don't truly know the exact coefficient of drag on that plate since I didn't do any real testing. And there's just other small factors such as, it didn't seem like the plate was, held totally straight. There was kind of a slight angle to it. But yeah, generally the results kind of follow the drag model much more closely. The drag model kind of predicts a terminal velocity since drag grows proportionally with velocity. The gravity model just kind of has the velocity increase more and more as it goes down. And that's kind of because, at a certain point, as the velocity increases, the force drag will kind of equal out with the force of gravity, so the net force equals 0. So the velocity does not increase anymore. That's kind of the reason why you see that. And since, this question is kind of asking what happens if you throw a plate down with a certain velocity, and I said since the drag model seems to more closely match reality, and the drag model kind of suggests that there's kind of a velocity after which it's kind of difficult to increase the speed unless the plate is thrown down with a very great force that is kind of greater than whatever terminal velocity that is kind of common for that object. it will likely have the same terminal velocity, but you could exceed the force if you threw it down with a very great velocity. Then the final velocity would be different, but the terminal velocity will be the same, in which the force of gravity and the force of drag kind of equal out.